So now we finally get to address what happens if we don't have ideal solutions. And what we're going to do is we're going to invoke a lot of thought processes and arguments that we made when we discussed fugacity, because we have some math that we really like. We came up with a bunch of different thermodynamic properties based off of using Raoult's law and assuming that we have an ideal solution. So a lot of interesting math. But, all right, what happens if Raoult's law is not followed? What we introduce is a concept of an activity, all right? And the activities that we're going to discuss this semester are activities based on a Raoult's law standard. Activity, just like fugacity, takes the place of concentration in our actual mathematics to keep the mathematical forms consistent, all right? But still dealing with real behavior, right? Now you'll hear me say real solution, you'll hear me say regular solution. Both those things just stand in for non-ideal solutions. So when we have non-ideal solutions, what we need is a way to account for the non-ideal behavior, and we do that with activity. Activities are effective concentrations, so they're standing in for concentrations, but also that's kind of like also activities give us like an idea of what concentration looks like relative to the standard, right? And I'm going to try to make that point when we actually get some mathematics going, but it kind of takes the role of concentration mathematically, but it does tell you what the effective concentration looks like relative to your standard. And again, I think that's easier to understand when we get numbers actually in front of us, okay? So fugacity was something that was very complicated, all right? But again, what did we do with fugacity? We just substituted in for pressure, and those pressures then actually were in situations where it wasn't ideal. So fugacity was letting us maintain the actual mathematical forms that we had developed. It's the same idea here, all right? Again, one more time, we're doing this relative to a Raoult's law standard. You'll see in your book, and you can read about it. I'm honestly not going to ask you questions on it, but you'll see in your book that for solute particles, all right, we really want to use Henry's law, and you'll see your book reference Henry's law in the graphs. We have no time for Henry's law this semester, okay? So we're always just going to kind of focus in on a Raoult's law standard when we invoke activities, okay? So that's the general idea of activity. It's standing in for concentration. It does give us information about an effective concentration, all right? And allows us to keep the mathematical forms consistent. It's accounting for real or regular behavior away from ideal behavior. So we're going to follow some examples from your book. We're going to kind of use an example system to do this discussion. And near like page 990, 991, 992, all right, what you'll see is your book is analyzing this chemical system. It's making a binary solution by mixing carbon disulfide and this, let me get the name right, dimethoxymethane. And what you'll notice from the Raoult's law curves is that there's a positive deviation. Now this makes sense. If you look at what carbon disulfide looks like in terms of its geometry, it's a linear geometry, so it's non-polar, right? Dimethoxymethane, right, I believe looks something like this, right? So this has both polar and non-polar parts to it, okay? So then there are no sort of attractive interactions here beyond the induced interactions. Here there's going to be some induced interactions, and there's also going to be some dipole interactions. When I bring these guys together, all right, this guy doesn't have any repulsive actions if it's interactions if it's by itself. Now, all right, what we get are some induced dipole to permanent dipole interactions showing up that are repulsive, okay? So for this situation, what we see in the Raoult's law curve and what we get from our analysis of the interactions is that there are actually repulsive interactions that exist. when this non-polar object, right, is in contact with the polar object, there's going to be some repulsion there. All right, so we actually get a positive deviation. So we get repulsion because of this mixing interaction that occurs, and so we get a positive deviation to Raoult's law. So everything that we said with respect to ideal solutions, it's not going to apply to this solution. So with that in mind, and you see that on the curves, all right? With that in mind, and like I said, the curves that I'm referencing, figure 24.15 in your book on page 992. All right, you'll see positive deviations like we discussed before, right? So then we go and we think about what the chemical potential looks like, right? And the chemical potential formula, right, for either one of the components, and I'm just going to label it component I, right, looks in solution, looks like, okay, the pure version, right, for the chemical potential in its liquid state for that species. Excuse me, let me just rewrite this. Plus RT, the natural log of P over P star. So remember in our derivations, we stopped here and we said, hey, listen, this is the truth. This is what the actual chemical potential is. This is what we can build both regular and ideal solutions with. We can deal with their chemical potentials with this expression. Then from there, we analyzed this and we made it a concentration because we assumed ideal behavior. So now we cannot assume with this positive deviation that occurs, we cannot assume that Pi over P star is equal to chi I. We can't do it for either one of these guys because there's this repulsive interaction that occurs. So what we do instead, because we like this mathematical form so much, is it's not chi I. What we do instead is we make Pi over P star into the activity, small a, for that component I, right? Now remember the substitution we made for ideal solutions. This chi I just came in here, right? Now instead, for these regular or real solutions, what we're going to do is we're going to replace this, right, this value, this fraction inside the natural log, with an a sub I. Okay. Now you can kind of see some properties of the activity already, right? Just from kind of looking at this. Okay. The activity, all right, for a pure substance, right, would be P star over P star, which equals 1. Right? The activity of a pure substance would be equal to 1, and that's an important thing to know. Also an important thing to know is Raoult's law is generally followed best when these concentrations are high. So based off a Raoult's law standard, and only for a Raoult's law standard, A sub I approaches chi sub I. It approaches ideal behavior as chi sub I gets big and approaches 1. All right. And I'm just going to remind you of the way we drew some of those deviations that occurred. I'm just going to make a quick little Raoult's law sketch here. Okay. What we said was here was Raoult's law, and when we showed a positive deviation, this will be like chi sub I. This is P sub I star for the pure species. Right? When we showed a positive deviation, we made a bulge, and then we kind of did this. So right here, what we see is the activity is approaching the actual concentration, because notice that these lines are coinciding. At these high concentrations, Raoult's law is being followed by our system. So in that case, if Raoult's law is followed, this just reduces down to our ideal form, which is really good. But now look at all other parts of this curve, all right? Is Raoult's law being followed anywhere here? Well, no, there's a large positive deviation between the actual pressure. This black line is like the actual pressure, all right? And the blue dotted line is our Raoult's law line if the solution was ideal. There's a deviation here, so are we going to be able to put a chi sub I inside here? Nope, we're just going to leave it like as the activity, okay? We can actually put some numbers to this using information from your chapter. And then we're also going to emphasize the idea of how it's an effective concentration. We see that it took the part of concentration in our formula, but let's actually, like I said, put some numbers to it. All right. Now, what your book will do is they will calculate activities based off of different standards. So when they do a Raoult's law standard, they'll use a superscript R to say, hey, that's the standard we're applying for actually talking about deviations from the ideal behavior, the ideal Raoult's law behavior, all right? And so there's a certain sample of this solution that's being analyzed. And this sample has a chi for CS2 that's equal to 0.6827. Now that means that the chi for this dimethoxymethane, which I'm going to just label as chi di, right? This is equal to 1 minus that, which looks like 0.3137, okay? So now this is the actual concentration, right? The activity is defined as, right, for species I, the actual pressure, right, over the pure vapor pressure, right? Now, if your A actually equals this, right? So let's say we'll calculate A for CS2. If A for CS2 equals this, then we know that we're dealing with an ideal solution, okay? If A is different than this, then we can analyze the result accordingly, right? So with this in mind, what your book does is they calculate A for CS2. And what they find is, all right, using table 24.1 on page 991, there's a vapor pressure table there. They find the correct P. They know what P star is for that given species. And what they find is A for CS2 is 0.7911. Okay? Now, this looks like it's greater than, right? It looks like it's greater than chi for CS2. Now think about how this makes sense. Remember what we saw? We saw a positive deviation. Okay, we saw a positive deviation. What did we say A was physically? It's an effective concentration. Well, what's the way, if concentration was the only control and you had an ideal solution, what would be the only way to increase the vapor pressure? It would be to increase the concentration, okay? So the fact that we see a positive deviation, it really makes sense that our activity is higher. Because if it was an ideal solution, the effective concentration would have to be higher to hit that positive value, that positive deviated value, all right, of vapor pressure, okay? So it really makes sense as an effective concentration when you think about how it compares to the standard situation. It looks like the concentration is higher in reality because you're getting more vapor. The effective concentration is higher. You see the same thing when you look at A for the dimethoxymethane, which is apparently a hard word to spell, right? And even say. So if we look at A, the activity, using this definition, and we find that pressure, and we know what the pure vapor pressure is, right? For this solution at these concentrations, what you get is an activity of 0.4727 using information from that table, right? Again, how does that compare to the actual concentration? It's actually higher. Why? Because there's that positive deviation in vapor pressure. Effectively, it looks like there's more stuff there, even though there's really not. Effectively, it looks like there's more stuff there because there's a positive deviation. Now think about how these arguments would sound if there was a negative deviation, all right? And then if you can reproduce those arguments, then you kind of get what activity is all about, right? So that's what activity is. It is a mathematical definition. We see that this is not equaling, right? Not equaling concentration. And in fact, a different value would be fed up in here. And you would see a difference, right, in the chemical potential because of that deviation from Raoult's law. Okay? Now, how we mathematically deal with these deviations is it's good to know about activity. But just like fugacity, there's an activity coefficient. Okay? And I know this stuff is conceptually difficult, so as always, just make sure you're writing down questions that you might have. Contact me via Zoom. We can talk about anything you need to. But just remember, activity is an effective concentration, right? There is something called the activity coefficient. And what we do is we spend a lot of the times, our time and effort modeling the activity coefficient. It just becomes a little bit more convenient way to modify or to model deviations and ideality, okay? Real quick, just looking at that positive deviation curve again, okay? Imagine you did some mathematical modeling here, and you're gonna model what P actually looks like as a function of chi, okay? And your book kind of does this. It shows you an example. So we know that P over P star for a given solution might be chi if it's an ideal solution, but it might not be if it's not an ideal solution. So in this case, we see definitely not an ideal solution. And they show you this example where it looks like this function is a better function for how P over P star is. Okay? Now, is this Raoult's law? Well, if this guy wasn't there, Raoult's law would be filed. But I see the modeling of this vapor pressure as it goes through chi. Remember what the units are here, your axes. Here's vapor pressure, here's chi, okay? Modeling this, I see, oh, I need to pick up this extra form to discuss what this looks like. Alpha in this case is just an empirical parameter we could set. The big thing here and why I'm showing you this is notice, is this Raoult's law? It's Raoult's law if that's not there, but to pick up on this functional form, we include this, yep, this is a regular or real solution. It's a non-ideal solution now, all right? And we see that if I would plug this in for activity, right, I'm not going to get simply chi1, right? I'm going to get this form, which is going to have our deviations from ideality. And that's what the activity coefficient is all about, all right? The activity coefficient, just like our fugacity coefficient, it's defined as the activity of a species over the concentration of that species. Now, for Raoult's law standard, the concentration that matters is chi. But for other situations that we'll run into, so this is going to be gamma sub I. For other situations that we run into, what I want us to know, activity over cons, is that the general way we calculate a gamma, and we spend a lot of times modeling what this gamma should be, all right? What we do is we take activity over whatever concentration units we're using. Because we're using Raoult's law, chi makes sense here, all right? So in this context of this example, remember, I kept on covering this up and saying, well, we would have Raoult's law except for this, all right? What this measures, just like the fugacity coefficient measures, all right, deviations from ideal gas behavior, this measures deviation from your ideal behavior for your solutions. So this will be deviations from your Raoult's law, right? It's encapsulated in A, obviously, but this does it in a more formal way. In the context of this example, imagine we did this fitting, we figured out what the appropriate alpha was. This is the actual vapor pressure curve. In the context of this example, this gamma for this, right, would be the activity, right, which is, remember, P over P star. So this, what I wrote down, this actually is the activity, right? So the activity divided by chi gives me a gamma that looks like E to the alpha 1 minus chi 1 squared. Hold on a second. It gives me, all right, the deviations from ideal behavior. And that's why, like I said, we spend a lot of time focused in on there in terms of what it means, okay? Also note that in the context of a Raoult's law problem, okay, the activity is P over P star. Some students like to do like a substitution here to see, oh, what it looks like is the actual vapor pressure, right, over chi and P star. If I substitute in for A here, I get this. This brings up a really important point about gamma and our activity coefficient, all right? We know that if it's an ideal solution, P is chi P star. So gamma is approaching 1 as we approach ideal behavior. So the closer to 1 we are, the better. And gamma measures that, right? The closer we are to 1 that says ideal behavior down here, right? The better off we are, okay? When is this, following this example, right? When is this going to be, right, close to 1? Remember what we said about activity and where activity starts to look like concentration, right? In this Raoult's law curve, when chi is big, when chi approaches 1, this goes to E to the 0, and what do we see? Our gamma is approaching 1. If our gamma is far from 1, then we're far from ideal behavior, right? So to continue with the example from your book, using a Raoult's law standard, and looking at that CS2 in dimethoxymethane, I'll say it right at one point, right? Looking at that solution, what you get is they actually calculate some gammas based off the Raoult's law standard using those formulas that we just went over previously on the board here. And what they get for gamma for CS2 using our Raoult's law standard is we get 1.159 for that solution that had that particular chi of CS2. And for the dimethoxymethane one, right, what they get is a gamma of 1.490. And what do we see again? We see that when you look at your gamma, remember what this is. This is how activity compares the concentration for that species. And this is how activity compares the concentration for that species. What do we see? We see that we get numbers greater than 1. So if we analyze this in the context of an effective concentration, if this is greater than 1, then that's telling us that our effective concentration is bigger than our standard ideas would predict. Our activities are larger than our concentrations because of positive deviations. Okay? So it's kind of tough to grasp the first time. So you're going to rewatch this video, and I'll stress it one more time. You're going to make sure that you have these general ideas down, and you can do these simple calculations for gammas and for activities, and you can look at that table, or if I give you a different table, you know how to put the numbers together and then interpret them in the context of activity being an effective concentration. Also note that everything we said about ideal solutions goes out the window. So one thing I want to quickly point out, all right, like your book points out, is what about delta G for mixing? And we're only really going to kind of look at this, all right, for a regular solution, right? Remember that for an ideal solution, we could kind of approach this and say, hey, what does this look like, all right? Let's assume that we have this ideal chemical potential form that we can substitute in, and then we can analyze from there, right? It's going to be the same ideas here. Delta mix G is going to look like N1, mu1 in your solution, right? Plus N2, mu2 in your solution, so no change there, minus N1, pure 1 in its liquid form, right? Minus N2, pure 2 in its liquid form, right? Now I'm going to show you what we wrote before. What we wrote before, right, and you don't have to write this part down, but what we wrote before was when we did this math, we had RT N1, the natural log of chi1, right, plus N2 times the natural log of chi2. That was the expression that we had. Well, if we have a regular solution now, right, if we have a regular solution, what happens is these chi's, right, and this is the purpose of activity, these chi's aren't really what we should have there. What we should have, because it's non-ideal behavior, is we replace concentrations with activities. And actually, what we like to do is we know that gamma for a species is A over concentration of that species, or, all right, A is gamma, our activity coefficient, times chi. And what we can do is, in each one of these spots, we can make that substitution. And so what we get for this regular solution, right, is delta G mix. And fill in the algebra steps here. You'll have to do some natural log algebraic manipulations. Looks like RT, and now there's going to be 4 terms inside here. There's going to be an N1, all right, natural log of chi1, and there's going to be an N2, natural log of chi2. Well, that looks like what we had before, right? But now also on the inside here, there's going to be an N1, natural log of gamma 1, right? Plus an N2, natural log of gamma 2, right? So what it really looks like is we regenerate our ideal result, but now we see that there are deviations from our ideal result. If you go back to the last thing that we discussed, this right here was our ideal result. But what do we have more than that? We have RT times N1 natural log of gamma 1 plus N2 natural log of gamma 2. We have extra information there due to deviations from ideal behavior, which are encapsulated in the activity coefficient. Okay? Now, your book defines this extra stuff, all right? Delta G mix minus delta G ideal for a mixture. Right? Is equal to, right, all that extra stuff. So imagine you took that stuff that I just erased here, all that ideal stuff, and you bring it to this side, you subtract, right? What you're left with, ooh, I'm just gonna rewrite it up here. What you're left with is that difference in your regular solutions, Gibbs energy of mixing, and your ideal solutions, Gibbs energy of mixing. And that looks like RT, N1, natural log of gamma 1 plus N2, natural log of gamma 2, right? We call this over here an excess Gibbs energy, and it gets this funny label G to the E, right? It's our excess Gibbs energy. There's extra Gibbs energy due to, right, deviations from ideality. So the big take home points here, okay, are activity is an effect of concentration. What we do from a modeling perspective, and it is modeling, is we find a way to get gamma. Because once we get gamma, we're really talking about deviations from ideality. And what we often do in our mathematics is we say, yep, I'm going to replace concentrations with activities. But honestly, what ends up happening is you say, well, if I'm going to replace it with activities, I know activities are gamma times concentrations. So while it's true that those concentrations get replaced with activities, we really focus in on making this substitution so that we reintroduce concentration, but we have this gamma now that we can go ahead and model from a mathematical perspective. Next chapter is equilibrium. We're going to do some review of some Gen Chem principles of equilibrium, but when it gets to P-Chem, what we're going to see is equilibrium deals with activities and not concentrations. So these substitutions that we're making, we have to get comfortable with them because we're going to be making them again when we do equilibrium problems.